Hello there, it's exercise 8e. We're going to look today at what's called the central limit theorem. And the central limit theorem becomes increasingly important from now on. So let's get on with it. You'll notice it's all to do with the normal distribution. But we'll have a look at this properly as we go through this PowerPoint. So start off, let's do something we know. If I roll a die, obviously with just one dice, and I'm interested in what the score is on top of that die. The probability of each event is obviously the same. It's a sixth, and that's, this is like a year 8 maths. That table, it's saying the probability of getting the 1 is a sixth, probability of getting 2 is a sixth, all of them is a sixth. And you could even put that into a pretty picture. This is what we describe as a uniform distribution, well, technically a discrete uniform distribution. And because there's 6 things that can happen, it's not unreasonable to call X is uniformly distributed with 6 things that can happen, and the probability of all of them, that is a sixth there. It's 0.1666666. And notice how they're basically all the same height. We can chuck these into our calculator effectively because it's a discrete random variable. We can put this into our calculator and work out the probability, or you could work out E of X, I suppose, properly. You could say E of X equals, it's 1 times a sixth plus 2 times a sixth. In fact, if you do all of that, it's 1 times a sixth plus 2 times a sixth, etc., etc., all the way up to 6 times a sixth. And I think you'd get, if you did that, I'm just trying to think, you're going to get 1 sixth, you're going to get 2 sixths, you're going to get 1 sixth plus, because you're timesing that by 8, you're going to get 2 sixths, you're going to get 3 sixths, all the way up to 6 sixths. Now those numbers, if you add them up, get 21, so that must be 21 over 6, which is 3.5. You could do the same thing. Remember, you could then work out E of X squared. I'm not going to do it. And then you could work out var of X, and that would give you the variance of these numbers as well. And this is when I did it. 3.5 it agrees with. When I did that, I got 35 over 12 and 2.92 for the variance. So that's fair enough. That's with 1 die. And then the obvious question is what happens if you get 2 die? And you're meant to get... what I'm interested in on this example is now not the total of the 2 dice. I'm interested in the mean of those 2 dice. That's why it's called sample means, I suppose. And depending on the scores on the 2 die, you could get a variety of different means. So if I get a 4 on one dice and a 3 on the other, I get a mean of 3.5. If I get a 1 and a 2, I get a mean of 1.5. And you quickly realise that in actual fact the lowest mean you can get is 1, because you get a 1 and a 1. Added together gives you 2, divided by 2 is 1. The highest you can get is a 6, because you get a 6 and a 6 divided by 2, you get 6. But you get all these different possibilities in between. And this is like that. The line of 7s you get when you add the numbers together. That's really all that is. So if you count those up and put them into a probability distribution table, you'll notice I've got 1 out of 36, 2 out of 36, 3 out of 36. They aren't all the same this time, because obviously some numbers are more likely to occur than others. In fact, 3.5 as a mean score is very likely to occur. Look at that, 6 out of 36, compared to 1 or 6, which is just 1 out of 36. Hopefully you're okay with that. And again, I could show that in the distribution diagram. And now it's definitely very much clearer that these are much more likely in the middle than they are at the extremes. If X takes a value at the extremes, it's unlikely to happen. The probability of X taking a middle kind of score, yeah, that's quite probable. So anyway, you can then work out the mean and the variance again, the same way as I did before, 1 times this, 1.5 times this, 2 times this, and so on, add them up. And that gives you E of X, and find E of X squared, find var of X, and you get these. I get 3.5. Again, actually. Now, that's not unexpected in many ways. This fact that the mean stays the same with sample means is what we were kind of hoping for, I suppose. We've seen it before. Remember last time, I'm just going back, we got 3.5 and 2.92. So what did we get this time? We got 3.5 and 1.46. And that seems to me to be 2.92 divided by 2. It is 1.46. So although I've calculated it using this posh method, in actual fact, it turned out that I could have just halved what I had before. And so that's what I've written here. Notice the mean is the same as before, but the variance is half as big. Okay. Even more sample mean. So imagine now I've got 3 dice. And I want the same idea. I'm going to add up the 3 scores, and I'm going to find the mean of those 3 scores. And I've done this. You're going to have to take my word for this. This is not a table you see very often with 3 dice. But it comes around from the probability of getting a 1 followed by a 1 followed by a 1 is a 6 times a 6 times a 6, which is actually a 216th. And you can do the same with a 6, and you can do all the same in the others. You know, the probability, it's a binomial distribution as it turns out. So I get these probabilities, and as I say, to a certain extent you have to take my word for it. And as long as we're happy with those, you end up with this distribution diagram. And you look at this now, it's not quite so pointy as the last one, it's more curved. And that curvature is starting to look a bit familiar. Again, we can look at the mean and the variance. The means is 3.5, the variance is 0.972, and shock horror, if you do 2.92, which we had originally, and you divide now by 3, why 3? Because we've got 3 dice, you now get 0.972. So again, although I've done this via the posh method, actually I could have just jumped straight to it. And this kind of confirms the results we've seen from other sample means. If you have a sample mean where you initially have the mean to be mu and the variance to be sigma squared, then a sample mean E of x bar will also have the same mean. It won't change. At least that's what you expect it to have if n is big enough, I suppose. And the variance of x bar, well, we saw last time, that becomes sigma squared over n, and that's been confirmed by the results I've done today. You get smaller, it becomes more reliable the bigger the sample you take. Now the thing that I notice most about this, the biggest surprise, is this idea that these things become what I think becomes more and more normal. Now it says here that these are distributions become more and more normal, and this is definitely not like a used in an English sense of, you know, it's just normal. This is a very much mathematical word. It's becoming more and more normally distributed. So this is what we had for 1 die. This is what we had for 2 die. And you notice initially it went straight across. It was a uniform discrete distribution. Here it's quite pointy. Here it's becoming definitely more curved. It feels more curved. And the more times I do it, the more normal it becomes. The greater n is, the more normal the distribution is. And that's what I want you to take from that this was not an accident, that this started to getting more of this shape. It was definitely more normal. Now I want to tell you then about the central limit theorem. Now the central limit theorem says for any sequence of independently identical random variables x1, x2, x3, etc., etc., with finite mean, which means, you know, it's a known mean, and non-zero variance, then provided n is sufficiently large, x bar has approximately a normal distribution with mean mu and variance sigma squared over n. These last 2 bits perhaps don't surprise us. This is what we kind of come to expect. The weird thing is this idea of it becoming a proper normal distribution. And notice it doesn't claim to be anything about these values at the start. It doesn't say it must be normal to start. It doesn't say it must be binomial or Poisson or something like this. Any values that we take as a sample, the sample becomes normal, assuming n is sufficiently large. Now, in practice, as far as we're concerned then, what does that mean? In practice, the central limit theorem says that no matter what the original distribution is, the distribution of sample means will be normal as long as, look at that, we've got a value from the exam board. They've said that as long as n is bigger than 25, then we can assume the central limit theorem works. So here's an example of what I'm trying to do here. It says a girl eats on average of 1900 calories a day. So look, it doesn't tell me anything about the distribution, just says she eats 1900 calories a day. And a standard deviation of 400, so sigma equals 400. What's the probability in a month of 31 days? Notice it's bigger than my magic number. It needs to be bigger than 25, so I'm going to write that straight away. And she does this for more than 25 days. And therefore we can write, therefore the CLT, this is often an abbreviation used for the central limit theorem, can be applied. So the central limit theorem applies, therefore x bar, because we want to know how many on average she eats, how many average she eats per day, x bar is normally distributed 1900, notice, normally we write 400 squared, but because this is the central limit theorem, we know we divide the 400 squared by 31. 400 squared by 31, I've just done it on my calculator, that is x bar is normally distributed 1900, comma, and it seems a very big number, but of course I've got to square root it in order to get the standard deviation, 5161. Now, it says then we want the probability that x bar is more than 2000. So if I just remind you what we do on these, we've basically got a normal distribution curve. We're expecting to get 1900, and we want to know what the probability of getting more than 2000. It's that probability I want. So if I just do this on my calculator now, I'm just going to put it into menu, and it's 7 on the Casio Class Wiz. It's a normal CD, so press 2. The lower bound is 2000. Upper bound is just a big old number, putting 99,000 odd in. Sigma, what was sigma? No, it's the square root of 5161.29. And mu was 1900. I expected to get 1900. And it should tell me my probability. The probability of being that big equals, according to my calculator now, 0.08, or 20 if I round to 3 significant figures. Don't know if that's correct. That is correct, so that's good. Okay, so that was relatively straightforward to do. Next question. A continuous random variable has mean 2/3 and a variance of 1/18. A random sample of 100 observations are taken, an x bar. So x bar we know because it's more than 100. N is greater than 25. Therefore we can use the CLT, the central limit theorem. Is we know it will be normal. The mean will be the same as before. That won't change. Never changes. What will happen to the variance? Well, that will become an 18th. And I've got to divide by n, 100. Which is actually a normal 2/3 and an 1800th. So that's what I think those are for the mean and the variance. And the probability then, again, I think this is just a normal distribution where I'm expecting to get 2/3 as my mean, and which is obviously 0.666, and they're saying what's the probability it's less than 0.68, which is slightly on this side. And I want less than, so I think I need this probability. That's what I'm finding. So again, I go to my calculator and I type in the lower value, and this time that's the negative 99999. My 0.68 is my upper bound. My sigma is, that's a square root of 1 divided by 1800. And my mean is 2/3. And I get a probability this time. I'm not sure if it's right. I get this to be 0.714. Let's see if it is right. 0.714 is right. Now I've got one more question. I don't think I'm going to get a chance to do this properly now. It might be useful if we have a look at it next time. But that's our introduction to the central limit theorem. So just remember, please, I'll just scroll back to the central limit theorem. This is the critical thing then. This is what we're going to apply. If we have a situation where we're finding the mean of a sample and the number of values we have is more than 25, then that distribution will become normal. And it even works if you just do a sample of a number of fish in the sea. We can still apply it there. So get ready to use this quite a lot in questions coming up. So we will go on to exercise 80 from the textbook, and we'll have a play with that. Thank you.